All right, hey everybody, and welcome back to the next episode of FISHBOWL.TV. I'm here with Julik. Hey, Julik.
Hello, man. Hello.
So, what are we in for this time?
Well, this time we're in for optimizing things. Like I said last time, we were making a blur shader, and the blur shader was very slow, which we came after at the end of the session. And so I said that probably it's time to see how we can make it go faster. And what we're going to use to do this is the multipass shader workflow. You know something about this?
I don't know much about it. From my knowledge that I have, I think that multipass refers to stuff you can call on that exists in the Matchbox language, like say normals or spec or stuff that's just been assigned from Autodesk. Is that kind of right?
Not quite. Actually, the multipass shader workflow allows you to do something pretty cool.
Okay.
It actually gives you the ability to sort of build a batch tree from your shaders inside the Matchbox node. So basically, you can grab multiple shaders and you can plug them together in a sort of a schematic. Only you never see an actual schematic. You have to write it out in code, but you can actually use smaller shaders within a bigger one, and you can connect the outputs of shaders to other shaders within your Matchbox. So it turtles all the way down, basically.
Okay.
But if we go with an example, then the way it looks like is normally you have your traditional Matchbox node, which has one input and which provides, say, one output for the sake of simplicity. Now, what you can do with multipass shaders is you can actually make a sort of a batch group within the shader. So what you can do is then, if we look inside this shader, then it allows you to do this, basically. So here our input comes in, our primary input, and then we take a little small sort of subshader and we process something with that subshader, and that provides an output. Then we also process that input with another little shader here. And then we can actually use a third shader to do some kind of rudimentary blending.
So is this kind of the equivalent of say the light wrap Matchbox? Is this does this refer to that?
Okay, as a matter of fact, if you look at most complicated Matchbox shaders inside, they actually use this workflow to a great effect, because then you can say blur here. So if we grab if you want to do, say, some kind of a beauty Matchbox shader, you can totally do, say, a blur here.
Yep.
And then you could do a high pass here.
And then you can have your comp after or something like that.
And then you can have your comp after, and then also what you also could do is you could supplement this with some kind of a matte input, and you could use that as a blending input for this one as well. So basically, the multipass workflow, it allows you to have multiple shaders within one node, and that's really, really useful. The only thing that you have to know when you dive into this multipass workflow is, first of all, there is currently no interface that will show you this diagram. So there is no way to visualize the schematic of this multipass shader. So you cannot actually open that shader and see how the inputs and outputs of the shaders actually combine with one another. You have to write them out in, as I said, in code. So in each of those shaders, you actually have to write out which output and which input in your pipeline you would like to accept. As far as I know, it will not protect you from circular dependencies. So it's meant to be acyclic, but it might become cyclic. So you could, in theory, write down that you want, say, I don't know, the output of this here somehow, which would make the system crazy. But in general, that's very manageable. And one way of using it is for for creating comps and for blending different effects. And another way is actually optimization, and this is what we are going to use it for.
Okay.
And I'm going to explain why that happens. So let's go for our paint thingy again. So like I said previously, for a box blur, it's called a box because we're actually using a blur kernel, which has this shape. Let's take a white one. Which, having a radius of 2, actually has a shape like this. Like so.
And like we learned last time, each time we add to that matrix, we get exponential.
Yeah, we get exponential growth. So like I said, we have to for a radius of 2, we have to sample. We've actually even made a little formula the last time, if you remember. But for the radius of 2, we have to sample basically 2 plus 1 plus 2 squared pixels. For a radius of 3, we have to sample 3 plus 1 plus 3 pixels squared, and so on and so forth. And so the number of pixels that we need to analyze for each pixel of our image actually grows and grows and grows and grows pretty much uncontrollably until it basically crashes the software or crashes the GPU or maxes out the GPU pipeline.
And that's why this lesson is actually pretty important, right? Because we're going to learn how to.
Yeah, we're going to optimize it. Now, the way we're going to optimize it is by using the quality of the box blur, and the a specific quality of a box blur. It's actually, it's sort of a mathy concept a little bit, but basically a box blur is a decomposable operation. So doing one time a box blur with a square matrix. So let's say we do this once, is actually providing you the same result as doing this first. So first we do our averaging on the horizontal 5.
Yep.
And then we feed the result of this operation to another convolve, which does the same procedure vertically.
Yep.
So it means that we can actually decompose this one pass with this square matrix into 2 passes, which are going to use one horizontal matrix for 5 pixels and one vertical matrix for 5 pixels. And a very neat property of this situation is that if we increase the radius, in this case, and let's see here, for example, if we have a radius of 2, then the number of sampling operations that we're going to have to do is going to be 2 plus 1 plus 2 times 2, because we have to sample once horizontally, then we have to save the result, then we have to load the result again, and we have to do the same vertically. But we don't have to do it squared, so we don't have to do it for 25 pixels, we only actually have to do it for 10.
So purely we're just doing the 5x and 5y and bypassing all the other neighboring pixels. Okay.
Yeah, that's correct. So and this and the performance gain that we'll be getting here is actually getting really big as our radius gets bigger, because if we go for 3, then we're going to go for 3 plus 1 plus 3 times 2. So here you can see that this one already gives us 16 pixels that we have to, no, sorry, not 16, 25. So here we would have to sample 25 pixels, but doing the same operation with the decompose technique, we would have to scan only 10. Or not 10, that's going to be 3 plus 1 plus 3. That's why I write this stuff out.
14, right?
Yeah.
Yeah.
And if we continue down that path, so this one is going to be 4 plus 1, so it's 5 plus 4, 9, so it's 9 squared. Yeah, horrible, right? There we go. And then for the same radius of 4 that we do in this way, it's going to be 4 plus 1 plus 4 times 2. So it's going to be 9 times 2, so it's going to be 18, right?
Yep. Is this something that you generally do on every shader, or is this more of a problem with blurs and stuff like that, or this kind of becomes a problem with any image processing?
Well, it really depends. It's usually applicable to blurs. It's also applicable to, let's put it this way, it's often very useful with convolves, like sharpening kernels and defocus kernels and bokeh thingies and blurs indeed, etc. But it's also very useful when you just in general have operations that you do on images which can be decomposed into multiple steps.
Yeah, and be done quicker, right?
Yeah, and be done quicker due to that. Now, in this case, you have to actually know that this operation can be decomposed in this way. But on the other hand, if you read any kind of tutorial about writing your first box blur, then it will mention that a very specific property of a box blur is that it's decomposable into a horizontal and vertical component. And if you combine them together, then you will actually receive the identical result as the box version that you do in one pass. So, and this is pretty much what we're going to do. So if we look at our drawing here, then for our case of a box blur, we're going to build a kind of a mini schematic where we're going to do our separate shader for the X blur first. Then we're going to take the result of that X blur and we're going to blur it along the Y axis afterwards.
Okay.
And that is going to become our actual comp output. So this is going to be our pipeline. Very simple one, just 2 components, nothing special.
Now I got one other question, just random question, but say with the new proxies on the fly, is that something that you would have to code into a Matchbox shader, or is that just something that the software does for whatever nodes are in there?
As far as I know, there are some features for degradation built in, but to be really honest with you, the last time I've actually used proxies in the software in Anger was a few years ago. But especially for you, I will research what's happening to proxies, because in general, there should be some workarounds embedded in the Matchbox pipeline to compensate for differences in sizes. But we can actually look at this as the next step once we're done with that, and then we can actually switch on the proxies and take a look.
Cool.
By the way, the proxies on the fly is in 2016, right?
Yes, I'm positive.
Is it only extension 2 or also 2016 usual?
That I'm not 100% on. It might be extension. Oh no, it should be extension 1, because extension 2 was only making Lustre GPU and new codecs. That was about it.
Okay, got it.
Yeah.
All right. So let's jump to our. Let's close some stuff that we don't need first. And then let's jump to our editor. So this is the shader that we coded the last time.
Yep.
As you remember, this one, the boxblur.glsl. And an important thing is that what you have to have your XML file formatted in a special way if you want to use multipass shaders. And what we're going to do to simplify that is we're basically going to just generate that XML file and let the shader builder binary take care of that for us, because it's relatively sufficient for what we want to do.
Okay.
So how do we make a multipass shader? Well, first of all, we are going to make a new file, and we're going to call it box blur decomp for decomposed. And then you set a dot in there, and then another dot, and then GLSL. This tells the software that this is a part of a multipass shader, just like this one that I've done previously for training. So every pass of your shader, every mini shader that you use in this kind of setup is going to be called your main shader name .1, for example. Okay. So if you want to write, say, a blur, just a blur, which would be the most generic blur on the planet, then you would have. Then you would have, it's too thick still. So you would have blur.1 GLSL. Then you would have blur.2 GLSL, and so on and so forth.
So I've actually seen this when I've browsed for the Matchbox sometimes.
Yeah,
where you can. Okay. So that's what that is.
Yeah, that's what that is. And the thing is that when you browse for a Matchbox, you actually open a file browser, which is one of the oldest components of the Flame software, still operational, I'd say.
Yes, yes.
And so what it does, actually, it's not able to collapse those components into one shader for you when showing them to you. And if you want to see those components as one icon, like if you want to see all the components of a shader as one thing, as one icon, or one title in the list, then you have to compile them to .mx, basically.
Okay.
We start with our first pass, and this is going to be the X pass. And so what we can begin with is we just grab the entire code of our shader like it was before, and we just paste it into this decomposed GLSL shader, so into the first pass. Then what we're going to do is we're going to see if we can actually make a blur which happens twice. All right, so to make sure that both passes work, what I start with is I grab the same shader code and I paste it into both mini shaders, both passes, and I ensure that I'm actually getting the result from processing the image twice.
Okay.
And that's
would that be a double blur, or would it just do the same thing?
In that case, it would be a double blur.
Okay. Yeah. Okay. Gotcha.
So what we're going to do is we're going to make a new file again, and we're going to call it box blur decomp.2.glsl, like so. And then again, we're going to paste the same code in here.
Yep.
And then we go to our terminal, and we ask the shader builder to build us an XML file. So the shader builder accepts two flags, basically. So the first flag you want is the X flag, which tells it to generate the XML, and the M flag tells it to basically to analyze the shader that's in the files and tell us whether we've done anything wrong or not.
Yep.
So we go for the box blur decomp in this case, and when you do this, you have to first. Basically, you have to list those files in order. So you start with boxblur decomp.1.glsl, and then boxblur decomp.2.glsl, and then we press enter and see what happens. So it tells us that it generated us an XML file, and now we're going to go into batch. And to begin with, what we're going to do is we're going to grab the Matchbox node, and we're going to plug in the shader that we have made the last time.
Yep.
So we grab our box blur and we set the radius to 8, say. So that seems to work.
Yep.
There is actually, I think there is a sort of a 1 pixel shift in here. Or in there. No, there ain't. And like I said previously, disable filtering always when working on pixels. So
Yeah, yeah.
And then we're going to grab Matchbox node again, and we're going to plug in our box blur decomp, which we have here. So as you can see, when you list them, when you look at them as a list of titles, then it is actually able to collapse them. Now, second, I think this has actually gotten better, because they actually, you see, they actually collapse those.
Yeah, they used to be. Yeah.
Yeah, then I think I actually haven't worked on 2016 much, but it looks like they have fixed it, which is really cool. So now it does show you a disclosure triangle here, but if you click on just basically this joined item, then it should go well. Yeah, you see? So we're complaining about things while things are actually have actually gotten better. That's bad.
Sounds like a typical Flame artist.
Yeah, exactly. Well, also, it's like you get used to things not getting fixed, and then you discover that they are fixed. Okay, I'm ashamed. I was wrong. I'm sorry. So now we've loaded the decomposed blur, and then we are going to set it to the same radius value of 8, like this one. And if we look at it, then you will actually see that we have pretty much the same output.
Shouldn't the decomp one be doubling, or is that something?
It should be, but it isn't.
Yeah, okay.
Because what we have done here actually does something very specific, and this is not something we expect to happen. So what it is actually doing, I will show you. And this is something that tripped me up a little bit, is that if we look at this from the perspective of this workflow, like a mini batch schematic happening within a Matchbox node, then we expect the pipeline to basically look like this. Or you know what, we can actually, I know what we'll do. We can actually draw this as mkeyer nodes because they're smaller. So we expect that it does this.
Then combines with the next one. Yeah.
That's what we expect to be happening. However, what's actually happening instead is this.
And I'm guessing this is because we have to assign it and tell it to.
Yeah, basically what happens is that all of those shaders, they share those names, okay? So what goes into the entire shader pipeline actually has a name, and those names are shared between all the components. So what we're doing now is effectively we're loading one shader which uses the input one, and that's the input one in this case. So it grabs the input one and pipes it into the first shader of the pipeline, and it also grabs the same input one and pipes it into the second shader of the pipeline, and we are getting the result of this one copy of our blur as the render. But this is not something we want. What we want is we want this link to be happening, of course. And so to do so, we have to replace the uses of the input one uniform in here with the uses of a special uniform which tells the shader pipeline to actually grab the output of one of the previous steps.
Okay.
So we have to tell it to basically load the result of one of the previous shaders in the pipeline as a texture. And to do so, we actually need to grab this little fellow here. Second, this is my thingy here.
Do you know of any, just from a programming standpoint, do you know of any tools that would help visualize this, like you were saying, in an easier way. Having the shaders like one next to each other, or do you know what I mean? To see the link more.
I don't think so actually, because primarily because those shaders use names which are specific to Matchbox.
Gotcha.
So some third-party tool wouldn't be able to figure out what those uniforms actually mean. But I would imagine that if Autodesk wants to push Matchbox even further, then at some point they might arrive at some kind of a combined schematic code editor, a la Quartz Composer or something. Excuse me, or something in the vein of one of the many shader node graph editors that they have in like 4 3D applications that they sell.
Yep.
Because I think they now have a shader editor in Maya, a new one. Relatively new one. It's been introduced, I think, 2-3 years ago. They have a nodal shader editor in 3ds Max. I wouldn't be surprised if that bleeds into Flame in one way or another.
Cool.
So to get back to this again. So like I said, we still use input 1 in part 1 of our shader in the first subshader component, which is here.
Yep.
However, on the second one, we have to replace the input 1 with a uniform which is called ADSK results pass 1. And the 1 in the pass 1 actually refers to this number here. So if we want to use the output of a component 1, then we say ADSK results pass 1.
So it's always based off that number we define.
Exactly.
Okay.
So now we have replaced it, and I think we can try to load it again. Let's see if it does anything. No, it does nothing. It's broken, and I can tell you why it's broken. Or can you tell me why it's broken?
I can't.
Okay. We have replaced the texture that we sampled from, the name of the texture, here. But we are still trying to sample from it here, actually.
Okay, so we have to copy paste that within those guys.
Yeah. So
gotcha.
We also have to be sampling from that input in the main function of the shader. So we grab the ADSK results pass 1 and we paste it into here. So let's try that again. Okay.
Okay, it looks like it's working.
Yeah, it's really blurry. So this one is on radius 8 and this one is on radius 8. If we actually do a quick difference between them. Then you can
we could also duplicate the other guy and double it up, right? Would that be the same thing?
It should be the same, yeah. Let's try that. Always good to verify your assumptions. And so the difference mat again.
It's pretty close.
Yeah, there is a pixel shift in there somewhere in the sampling, which will leave to the readers to pinpoint. Because I think I've just made some offset mistake and minus plus by 1 pixel.
Yeah.
But in general, the result of the blur is actually the same. So now what we're going to do is we're going to do the actual decompose operation. So what we have to do is first we go to our first pass here, and then we're going to make it only blur the horizontal stuff.
Mm-hmm.
So we know that it walks the horizontal pixels with this thing, with the offset X.
Yep.
And we know that it walks the vertical stuff with the offset Y. So what we're going to do is first we're going to remove all of our nodes here because we're not going to need them anymore.
Because that stuff was calling out every neighboring pixel, right?
Yeah, this was calling out every neighboring pixel, and those are 2 for loops nested. Mm-hmm. So basically for each offset in X, for each offset in Y, do this addition.
Yeah. Yeah.
So now we remove this stuff, and we change the number of neighbors function. Sorry, the number of neighbors variable, because previously this determined how many pixels we average together, and we actually needed the whole lot, like the entire box.
Yep. The
of
whole
pixels.
grid. Yep. Yep.
But now we can actually go just with this. And I always put braces in arithmetic to quickly understand in which order the operations are going to be performed, because usually, like in general, there is a certain standard order in which arithmetics are done in computer languages. Most of the languages conform to it. So when you have something like x times y plus z divided by 14 multiplied by whatever, some people actually know by heart in which order those operations are going to be performed. I always forget, or rather to say, for me sometimes it's a little bit like it's not a mental effort I like to have. So when I have arithmetic, I usually try to specify it with braces on the spot, because then it's immediately obvious what's going to happen first and what's going to happen last. So
another thing to help you if you ever have to pick it up.
Yeah, because
later.
Because you know that to evaluate this thing, it has to actually evaluate this, because it has to open the braces first, and then it has to do the +1. Then we are going to remove the y sampling, and first we're just going to kill this variable, the opening part of the y loop, like so. And we're also going to replace the offset y variable, which we don't have anymore, with 0, because now we don't actually move our little sampling box up or down. So the offset on y is always going to stay 0.
So do you have to always have that in there, like because it is xy, or like you?
Yes, you have to, because this is xy, and because we are doing a subtract from a vec2.
Okay.
GL record xy is a vec2, so when we subtract something from that, it also has to be a vec2.
Gotcha.
But if we subtract 0 from the y coordinate of the GL record, it's the value of the y, it's actually going to stay the same.
Gotcha. Yeah.
So we replace it with a 0 in here, and then we also go into our second pass, and here we're going to do the same operation. So we know that we can actually do this like so. And then we're going, in this case, we're going to remove the outer loop, which does the sampling in y, in x. So in this case, we're only going to keep this guy, which samples vertically. And in this case, the offset x is going to be 0, and the offset y is going to end up being used to move the sampling window up and down.
Yep.
So we put that to 0, and I'm also going to shift this to the left so that it looks nicer. So in the end, what we got is we have one pass which does a blur in x, and another pass which does a blur in y. And the only thing that's changing is actually where we do the offset and which dimension we have to plug into the vec2 that we subtract. So that's pretty much done. And now we have to load it and see whether it will work. I'm curious. Yeah. So it gives us a blur of a radius of 8. This thing also gives us a blur of a radius of 8.
And will it become pretty apparent once you start going to higher values, right?
Yes, but first we have to compare that we really got the same result.
Yeah.
Which we do. So this is actually this is actually the case where, thanks to the glory of mathematics, you can actually decompose an operation into 2 steps, and you come out with exactly the same result. So this worked. And then indeed it's going to become really apparent where this goes once we ramp this up to 32, say. See, it really took a while. So if I go to 1 in here, and then I go to 32.
Because it's, because we're sampling all that extra stuff.
Like that. And if we do that here, and we go to 1, and we go to 32, let's see how long that takes.
Wow. Oh, so it's crazy.
So there. That's basically one of the ways to optimize a box blur. Some other blurs, I think the Gaussian blur also decomposes in a number of ways.
Mm-hmm.
So you can actually play with that, and for some situations it's really, really handy, because this one we can actually ramp up to 128 or so. Let's see if that will work. Let's see if we can crash the machine.
That's still very quick.
Yeah. So that's 128. And also what's funny about this is that the box blur actually has a nice property, an interesting property, that the box blur is actually stamping. So once you have a box blur which goes to say 50 or so, then it almost starts looking like a sort of a bokeh-like effect.
Yeah, like a lens blur kind of.
Yeah, like a lens blur kind of thing. Whereas in practice, it's actually it stays very, very fast. So this is something really worth it to play with. And also, actually, the funny thing is that when I was starting on Flame way back, no, not way back, but sometime back, then I was told that if you actually want a very quick way to match a defocus in action, if you really, really have to, then sometimes it works much better if you just go for a box blur in action, because it's more likely to look a tiny bit more like a lens blur.
Yeah.
That was before the lens blur nodes actually came to be, etc. But
where you could feed your own custom bokeh shape
and all that stuff. Actually, there, if you go to the Logic Matchbook site, you will find some nice stamping bokeh stuff from Ivar, which is really, really cool. And I think he's working on something in that vein right now as well, trying to create some kind of a nice stamping bokeh stuff. Actually, most of the quick stamping bokeh shaders, they're based on those kind of smart convolves that you can decompose into cheap operations.
One question, when I've seen some other shaders, say from the Logic Matchbox site, say to do with blurs, I think it's not an Ivar blur one, but it's a different blur. It's a depth of field one, but the thing, you know how they have the samples you can add? Because by default it looks like really low samples on the blur.
Mm-hmm.
Is that the same kind of like, would that be based off a multi-pass thing like this, like by combining those, or is that another function altogether?
I would imagine that it's also based on the multipass, but the multipass implementation, whether you are using it or not, it has more to do with it actually has more to do with the algorithm that you want to apply. Because in this case, it's just so that this algorithm decomposes in this way. However, you have to sample this from the result of this for that decomposing to work. So in this case, you have to go multipass, because you need to have the result of your first step as a texture to address the pixels from that. So in this case, you have to use multipass for this decomposition. But in general, you could also write a lot of those operations in code. Basically, you use multipass if you need to address a pixel result of some other previous operation that you did.
Okay.
All right. So, and actually what's beautiful about the shaders on Logic Matchbook is you should just read them. So if you're curious how how say the Z depth blur works, then you most likely just can download it and just look at the code and just read the code and try to decipher it. And I am pretty certain that any shader author would take the time to explain how he arrived at a certain result, or in any case, what has he exactly copy pasted from Shader Toy to make it work the way it does.
Cool. Well, that's a great thing too. Besides the Logic Facebook, there's the Logic Matchbox dev too, where there's heaps of people always willing to help.
Yeah,
which is cool.
Yeah, there is Logic. There is Logic dev. I think it's also a closed group, but if you want to get there, anybody on Logic can get you in there.
Cool. Well, that was amazing how much quicker that is with that really quick kind of optimization.
Yeah, I was also pretty surprised, but I must admit I'm not really good with this sort of math tricks. I guess Lewis Saunders would be your man if you would want to get into that area, like really smart optimization stuff and playing with those things.
Cool.
Well, awesome.
Well, thanks, Julik. I'll see you next episode.
Yeah, we'll see each other.